Hello, so I'm Alvin and today is another day, so you'll probably be expecting another video to come up. Well, there is going to be another video coming up, but this time, I forgot my times table. Anyway, I have a times table over here. Let's see. So this is a times table, and this times table is an 8 times 8 times table. And now I'll give you 1 minute to memorize it. A 1 minute timer, right? Yes, it's a 1 minute timer. And you go memorize it in that minute. Yes, you memorize it in that minute. 43, 42, 41, 40. And there comes a little rubber ducky, which always comes during the period. The secret is that I just tap on 1 and then the timer starts. But if I tap on any number other than 0, then it makes a that minute timer. However, if I tap on 0, then it actually sets the 3-second timer. 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And then I'm gonna close this. So now did you memorize it? If you haven't, probably there will be another thing to. If you haven't, probably you could memorize a much more bigger 50 times 50 times table if you would like to. If you want to memorize the 50 times 50 times table, I could share it with you. And it's over here. Over here. Good. So this is a 100 times 100 times table. And over here, you don't have to memorize it, but I'm just scrolling through it so you can see all the entries. Our paper is much more smaller than A4. Yeah. So over here it is page. It can be printed as 4 pages, or else it might be too small. So today we have a timetable and I have a task for you. Draw a circle and make 16 equally spaced points on the circumference. And then let's start by labeling any point 0 and labeling them clockwise, with each number 1 bigger than the previous one. So that is your task. And you stop labeling when you get to the first point on 32. So now label it right now. And I'm going to wait for you. I'm going to set another 1 minute timer. Good. 56, 55, 54, 53, 52, 51, 50, 49, 48, 47, 46, 45, 44, 43, 42, 41, 40, 39, 38, 37, 36, 35, 34, 33, 32, 31, 30, 29, 28, 27, 28, 25, 24, 23, 22, 21, 20. Do you say you're already done? 17, 16, 15, 13, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So time's up. And I hope that you have already done that. And the next thing to do is to connect each number to a double until you get to 16 to 32. I'll give you 1 minute for that. 1, 59, 58, 57, 56, 55, 54, 53, 52, 51, 50, 49, 48, 47, 46, 45, 44, 43, 42, 41, 40, 39, 38, 37, 36, 35, 34, 33, 32, 31, 30. Done already? I don't believe you. 26, 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 17, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Time's up. And now that you've connected each number to a double, I'll give you 3 seconds to see the pattern. 2, 1, done. Okay, so now you probably saw the pattern that one of those it was clearly split into 2 regions where one of those only had a few rays and the other one was crowded up fine. So now that you've seen the pattern, I also did that, and I also saw the pattern. So to make you see it, I highlighted the border of the pattern with an orange color. And do you want to see it? Okay, then here we go. Ready to see it? In 3, 2, 1. Good. So this is the image that I made and then I also made orange lines that show it. That's probably not very clear. So do you want to switch to a clearer image? I've already done it with 32 points earlier, so you can see that. Yes. There. Now the pattern is so clear that I probably don't have to outline it in orange for you. Here's a much more rougher one by only using 8 points. Or isn't there? I remember I did it, but anyway, that was very clear. So we just take a look at this, but I have an even clearer image that uses 64 points. See it? Here it is. And I also labeled all the points. So that shape does look a lot like a heart, right? And luckily for me, I remember my times table. So that's called caridoid, and it doesn't only pop up in that place. I make a new tab and not this. Okay, so this is a triangle, right? No, I don't want a triangle over here. Let's see, wait for it. So that's the image of the mandelbrot set. It is generated using iterations. So just in case you're a little curious, this is an image of the mandelbrot set. And why did I show that to you? Well, the biggest thing on it is actually a perfect carotid. Also, the second one is actually a perfect circle. Okay, and suppose you have a circle. You have two circles and a pen. You tie the pen to one point on a circle and then roll the circle around the other circle. When you're done rolling it around, if the two circles are the same size, then you get an exact carotid. So that's a mandelbrot set. Cool, right? Is it cool? Probably yes. Mandelbrot set. These are the iterations. And how was a mandelbrot set formed? Are you asking me? If you are, then I'll tell you the answer. The mandelbrot set was formed by first I give you more images for you to understand. This is a 2D and 3D. This is what it looks like in 3 dimensions. And when it's in 3 dimensions, the middle line turns into the logistic map, the natural growth map. That one we better zoom out on. Let's take a look at it. 1. And these are lines that connect it. And that one is a 3 because it has 3 thingies on top of it. And that one has 6 thingies. That also has 3. And that has 4. Can you see the 4th one? Or can't you? Well, that one is a 7 because it has 7 thingies on the top where it's split. So now this one has 3 thingies on the top, and this only has 1 thingy on the top when it splits. Obviously this. So the pattern continues over here. With more and more thingies. Yes. So let's go back. Good. So that's the image. And this is a much more clear image. Right? Is it clear? So I zoomed it out for you, and now you can probably see it. So each one is the sum of its 2 neighboring ones if it does have 2 neighboring ones that are both bigger than it. But if their neighboring ones are smaller, at least one of them is smaller, then that means that it isn't the sum of 2. Okay, so here's the picture again. And this is, well, this is what you get when you zoom in on the main one. And you probably see that there is a ratio between one bulb and the next. So this is a zoom in this is a zoom in picture on this. And then you zoom in through this, which is commonly called the seahorse valley, and then into one individual seahorse. Well, that is like the seahorse tail. It's also called the Mesorex point. And there is exactly one path which goes through the tail. And as you zoom in, and over here, as you zoom in into these parts, then, hey, wait. Then you get this, another mandelbrot set inside. You can continue the zoom in for the second order, but So that's a seahorse, but there are also beautiful patterns. And this is the island in the middle, and this is this one individual island, while this is one individual spiral. And this is what you get when you do the mandelbrot set for powers of 0.002. And this is also a 3D Julia set. Silly, right? So the mandelbrot set is generated by picking any complex number and then start with z equals 0. And there's a function f of x f of z which takes d squared and then adds a complex number, where z is a complex number. And then you start by putting z equals 0 and then keep putting the output as the input. And if it does explode, then you count it out of the mandelbrot set. But if it doesn't, then you count it in the mandelbrot set on the complex plane. That's how it was generated. That's the tricorn. Good. So this is the entire article. The mandelbrot set. Good. Okay, now back to our times table. What do you think is so special about 2? Or perhaps there's nothing special about 2? Then you go ahead and label it 3 times until you do it with 16 points and label it until you get to 48 and then connect every point to its triple. And then you'll believe that nothing is special with 2. Or do you want me to show an image of it? Want to? Then I'll do it. Okay. So, what do you think about it? Do you want or do you not want? Just in case you want, then I'll share it with you. That's it. So this is the image, and I lost all the points. So C segments connect each number to its triple, and you see I labeled it all the way up to 96 because I used 32 points. So there's nothing very special about 2. The only thing special about 2 is that it produces a shape name, and its name is called a caradoid. It also is, this shape is also very special, and it's called a neophyte for kidney. Neophyte and kidney don't sound pretty alike, right? It isn't very like. So, but it kind of looks like 2 caradoids mushed together. Don't see it? One caradoid over. Oops. I better make it hollow. One caradoid over here, that is. And another one over there. And it only contains of the part that contains them both, right? So this is what it looks like. I didn't have enough time, but if you have Then you could do it for 4 or 5, and it looks like a flower with more and more petals. Well, and when the number gets up to 45, then or 34, then the middle part looks like 2 caridoids smashed together. So now we'll see a movie, right? Yes. And when we get to the very end, you'll see a movie over here. You'll watch it.
A little bit slower than what we had before.
Beautiful, isn't it? I have to make it faster because we don't have enough time. 2. And our full screen continues. And it seems like things are spiraling into the middle. And the end is what happens. And at the end, it was a very fascinating picture. It's one that the number you're doing is 51, close to a quarter. And when you do it for any even number m, then 1 less than half of m produces a checkerboard. Not a very good approximation, right? Maybe you could go ahead and watch more videos on MathLogger, or maybe you could watch the whole video. Anyway, there are some common points for all of those. When you're doing times table m, then on a number that is mn, then each multiple of n on it always goes to the opposite side, and that is a line of reflection. And it doesn't change. And there are very special things. For example, over here, we could.
That's cool, huh? And now I've let it go.
So there. So it looks like.
Okay, or actually do the transition continuously. So let's show you if I just do the multiplication times 2.1, what do you get? 2.1, 2.2, 2.3,
yes.
2.4, 2.5.
That's
2.6,
what
2.7, you can kind of see how cardioid turns into a snapshot, which is kind of cool. Huh? And now I just let it go, and numbers are going up, and you can see the petals going more, right? So it is continuously. And when you think, well, that's probably what it's going to be, you can also look at this in the mandelbrot set. You can actually see exactly this sort of pattern happening in the middle, and if you kind of push the exponent to infinity, the whole thing kind of turns into one big circle. That's pretty cool. Okay, let's, I think that's the end of it, but no, let's just keep going here. Right? The petals are pretty much going to go away now. But if you just look at what's happening here, you see there's a lot more structure somehow being hinted at, right? I mean, we're moving very fast at the moment, right? We're moving very fast. But if you actually went through this frame by frame, you would see a lot of really, really nice structure happening. And I've highlighted a bit here. So just a few of the frames that you get, some really amazing stuff happening here. So you stop at 33, you get this one, you stop at 34, you get that one here, and there's a couple of other highlights.
So this is what happens if you just look through the individual frames. These numbers are too small to read, but just wait for it.
There's a lot more. This is how many I could fit here. Huh? Okay, and maybe have a close look at some of them. Okay. So here we've got 4.
These are 4. The first one is 2, which is a caridoid. I remember we talked about it, right? Or didn't we? I remember we did. And this is 34, where it does look like 2 caridoids smushed together in the middle. And if you look very carefully, you still can see the petals. And this is 51, it's like a circle. And this is 99, so let's watch it.
Now the number that always corresponds to is actually 200. Okay, 200.
Yes, so those are all produced from 200.
Doing here has a special name in mathematics. Okay, so what we're doing here is we're doing the times table modulo 200. Okay, so it's a special name. It's actually incredibly important in all sorts of applications to do this sort of.
Maybe you could try it out yourself. What will happen if you put all the times tables together in one big circle?
Modular arithmetic. Okay, but anyway, for our purposes, you understand how it's built up, and if you know a little bit more, you know a little bit more. Okay, so for 2 times table, we get the cardioid. For the 34 times table, modulo 200, we get this guy here. And then some other things, interesting things, for example, if you multiply by 51, we get this guy here. And if you multiply by 99, we get that guy here. And obviously, if you just look at the 2 numbers below, 51 is pretty close to 1/4 of 200, so it must have something to do with that. 99 is pretty close to 1/2 200, must have something to do with that. Okay, now I really want to explain something. I really want to explain where this one comes from.
So where does this one come from? Think you do not know? Well,
and
keep watching.
well, the first time I saw it, I was pretty surprised, like pretty much everybody sees it. But then I remembered something. I had seen a cardioid before in many different guises, and in one particular one that I was familiar with, I could see where the connection is. I just want to tell you about that. Okay, and it's got to do with this light rays bouncing around. It's a little bit different from what we had before. Okay, so basically,
yes, light rays dancing around. It's just that light rays
circle
dancing.
here, and then we've got a light source right over on that side, right? And that circle kind of reflects the light, right? So we switch on the light over there, and then well, what happens? Well, light rays kind of emanate in all kinds of directions, get reflected off the circle, right? Bounce around, and you kind of see this pattern here emerging in the cardioid.
And then there will be a caridoid.
So I knew this one. I had actually calculated the curve, from this prescription at some point in university. Okay, then they can actually really see very easily why the cardioid comes up in the 2 times table. I'm going to show you. Okay, so this is highlight, like one of those rays coming out. It kind of hits the wall here. Okay, and then it gets reflected at the same angle as it comes in. Right. So this angle here that you see here is the same as there. Right? You can see it kind of goes like that. Okay, so what does that tell us now? Well, if we put this line in the middle, it means that this side really flips over to that side here, which means that this segment here in particular is exactly as long as that one here. Right? So if I travel from this.
So if you labeled it correctly, then if this is 0, this is n, then this should be 2n, because if these lengths are the same and you use equally spaced points, then that should be.
This light bulb to this point, and then from this point to that point, it's exactly the same distance. Okay, so that's going to be important. Okay, so let's make this 0. Let's call this n. So what's 2n then? Right? So to get 2n, what we have to do is we have to measure this distance here, and then we have to measure it again. Where do we get? Right up there. And so it's pretty clear that when you do it 2 times, then you get that reflected ray, in the picture. Just to finish off, I'm going to show you a little bit of a movie of all this stuff evolving a little bit slower than what we had before.
So that's a movie we already watched, but first you still can see it, and so after all, the multiplication is not so boring, right? Or is it still? Escape. So that movie is very cool, right? Very cool. So you can also try and do it for 2.5 or 2.25 or 2.0625 or things like that, and make up your own movie of the number getting more bigger. And particularly, I just wanted to explain how it goes from 0 to 1, because 0 is everything coming to the 0, and 1 is just nothing. So how did it go from 0 to 1? Well, if you did it, anyway, if you did it, then 0, all of them went to, and as you slowly increase the number, all of the numbers trail from 0 to their own number. So that's where it came. How about from 1 to 2? Well, it's just that each of them trail to their double, and through that process, they make a curve. Well, for higher numbers, it's just that there's a line in the front of in one side of the line, everything stays the same, but on the other side, a new petal emerges. So it kind of looks like a flower. And if you push the whole thing to infinity, then the petals get closer and closer to the circle, and it just turns into a whole circle. Even though you could watch and see what happens in the middle. That's pretty fascinating, right? Right? Do you think it is? Yes. So if you have time, then you can also try it out. So maybe you could try it out with, well, the 0 to 1 I already explained, but you can still do it if you want to, but I better recommend 1 to 2 or 2 to 3 or something like that. So hope you have a good day. So it's actually that the checkerboard and the circle things are actually related to 1/4 of it. I had tried it out for a few small values, and it seems that it always is like that. So have a good day.